We can start. So welcome to the course Mathematics of Generative Modeling, and we are in the almost in the middle, slightly less than the middle. So we have like 25 classes, right? So yeah, maybe slightly more, maybe already. Okay, so so what we have done so far is we did a we have now a basic understanding of generative modeling. So what it is, right? So basically we are given some samples x1, xn, it could be cat images or whatever, and this is the real data distribution. In this case, let's say some cat images, and then we want to produce some new cat image, right? Let us say x bar that follows this given distribution of the cat. Okay, and we have seen some concrete methods by now. So we have seen something called generative adversarial network, generative adversarial networks, or in short it's called GAN. Okay, 2014, Goodfellow proposed this, and the idea was that you start from KL divergence and then you look into a generalization of KL divergence, which will be F divergence. Then in the F divergence there is a function f there, and you use conjugate twice, right? So use conjugate of f, meaning f star equals to f, then you bring the supremum out, supremum that is involved in the conjugate, out of integral, and when we do that you get a variational form. So recall those t operators that you got, okay, and these t operators it parameterized by phi that later turned out to be a discriminator. Okay, and then we were led to a min max problem where we had fx minus fy, okay, and we can also like do like this, where x follows p and y follows q, and then this became a min max problem, and we have changed the f to let us say the discriminator, and why we said that let us put this as g theta of z, where z is sampled from something known, let us say standard normal. Okay, then it becomes a min max problem in min max in theta and phi. Okay, and we are supposed to solve this min max problem. Okay, and so this was the key idea of the GANs, and then there was WGAN. WGAN is very similar to GAN. In fact, it's exactly the same loss as GAN, but the only thing is you have to introduce Lipschitz one Lipschitz continuity of the f function here. Okay, and the theory that it built, although it arrives at the similar min max problem, but the theory came via looking at W distance, which is the Wasserstein distance. In particular, we looked at W1 distance. Okay, and this was defined as the infimum over all the joint probability distributions with marginals P and Q so that the cost is minimized. In this case, it's 1 because I'm taking power 1 here in the cost. So this Wasserstein distance was then made tractable because this was not a tractable problem in the sense that and it will be some probability distribution here. Okay, so I'm measuring some distance between some probability measures and so on. Okay, I'm not trying to be precise here, but later here it was changed to something tractable via KR duality, and that that was supremum over h less than equal to 1, and then that became something like this. Okay, and then here the variation is created by these h, which are one Lipschitz functions. So and then I can parameterize this by some phi. Okay, I mean this is not exactly correct. Like this is like the so in general I can write this as cost of xy over pi xy. Okay, so this cost is what I define it to be norm of x minus y. Okay, anyway, like we will generalize this today, but so this generic framework comes from optimal transport. Okay, so this is what we are trying to infimize, the cost over all possible joint distributions P and Q. Okay, so it will be more explicit in the general notation today. The whole class will be about this today. So we will get deeper into these things today. But for the Wasserstein-GAN perspective, we arrived here by applying this with this cost. We got this, and this again became a min max, but the difference is like now we have this one Lipschitz continuity. And then later we said that later there was a theorem in the improved Wasserstein's GAN, improved WGAN paper to introduce gradient penalty GP introduce gradient penalty. And what this said is that there is a theorem that says that there exists an optimal solution for this, which is, let us say, H star. So there exists H star solution of KR dual form, and if it happens, then grad square H star is 1. So this motivates that introduce this constraint in the dual form. I mean dual form, or like yeah, this one exactly. So here we modified this, and then we added the gradient penalty, which is grad square h minus 1, and we can also make it a square. So we discussed all this in detail in the last class. That's not my. So the point here is that this is GAN, and then we had WGAN, one Lipschitz functions restrictions. You do the gradient clipping, or in fact the weight clipping, and that kind of implies in some way one Lipschitz continuity. And then you had improvement on WGAN by introducing a gradient penalty. And we proved in the last class that the directional derivative is 1, but we were yet to prove that given that the directional derivative of H star in the direction v is 1, how can be so that not grad square, sorry. Okay, this is just grad. Okay, this is just grad. So how can we show that the gradient norm of the gradient, I mean, okay? So gradient is a vector, it's norm of the gradient will be 1, okay? So we will try to wrap up this proof today, just to complete the WGAN picture, and then we will move to optimal transport, where we will go to generic framework, and via optimal transport we will derive another generative modeling, which is called Sinkhorn generative modeling. Okay. So this Sinkhorn generative modeling idea, what it says is that earlier you had the WGAN loss, and this WGAN loss was not tractable because you are supposed to do this for over all the joint probability distributions, and minimizing this is not an easy task. Then the KR duality gave you a little bit tractable form, where obviously H can be varied via parameterized neural networks. So this was one way to make this into generative modeling via KR duality and so on, okay, variational form and so on. Another approach is when what we are saying is that, okay, this is looking intractable, right? So can we do, rather than going to KR duality, can we have some way to make it tractable in some other way? Okay. In other words, can I compute the Wasserstein's distance as it is, okay, as it is in the sense like in this current form, without going in, without going there. I mean, the thing is here, by going to KR duality, it gives you a generative model for sure, okay, but in the current form, in the original form, okay, where we have joint probabilities involved, people have studied this problem in so-called optimal transport, and that's where computing this cost becomes a major problem there, okay. So and we need a algorithm that can do that, okay. Obviously here I am searching for H also, right, okay, so that I have to make supremize, and then this gives me the W distance. So there is a idea via Sinkhorn is the name, okay, where there was a proposal to have some tractable way to compute this. Now if I have a tractable way to compute W, then I can build a generative model by having W being computed between P and P theta. P theta is the distributions that I am trying to generate, and it could be, as usual, the way we do is we make it G theta Z, where Z gets sampled from the known normal distribution, and then the mapping from the normal distribution to the to G theta is learned via knowing this cost, okay. So this P is a real data distribution which could be estimated, let's say, okay. So if I know a way to compare P and P theta, okay, if there is a way to compare P and P theta, and which is cheap, okay, like solving this in a cheap way, then I can have a gradient descent method based directly on this, because what I will say is that I generate a random sample Z, it goes via neural network, and it generates some P theta. This P theta is compared with P, okay. If the so we will see the tractable algorithm in a more detail, but if I can compute this cost, then I will know how bad I am doing with the generation, and if I am bad, then I do gradient descent, update the theta, okay, and then with the updated theta I compute the Wasserstein distance again, okay, and then if the cost remains high, I keep doing gradient descent on this. So the main thing now goes into what exactly was done by Sinkhorn to make this tractable, okay? And that seems to be a direct approach where not necessarily an adversarial approach like min-max, but seems like I can go and just compute Wasserstein distance for whatever p theta I'm getting, and I keep updating my parameter via gradient descent until the cost becomes very less, okay? So this could be seen as a minimization over theta, okay? Obviously, I know you may have questions right now, but we will answer this. That's the whole point of this class. Okay, so so there is third style. So this is GAN, WGAN, and this is Sinkhorn generative modeling, okay? That's where I use WGAN loss, but I compute it in a direct way, okay? Until this, I mean, there in the current form it was not tractable until recently, and that is the reason why also you went via this approach and so on. But then, I mean, in the current form, it's difficult to solve, okay? So we have to make it, as such, it's a linear program because the constraints you have are linear basically. So if you see the discrete joint distribution, then they are tabular data, and basically you are saying that the row sums are the marginal p, column sums are the marginal q. So this is an affine constraint, and this is linear, okay? It could be written as C transpose X form, okay? So this is this could be seen as a linear program in the discrete sense, but then still you want to have because even with this linear program, there are difficulties, okay? So still we need ways to make this tractable. So far it's very high level, I know, but this is the plan, okay? We will develop some other generative model via so-called Sinkhorn algorithm, okay? So today we will complete this, however much time it takes, I don't care, but today we will complete this as a full topic in itself. Okay, so today you will also get a taste of bit about optimal transport, which is a more generic way to see things, and Wasserstein distance becomes a very special case. Now let us go to our first agenda today is to complete this proof, and the second agenda today will be to go to this, okay? So where I left last time, it was a simple step, but I think we were having a lot of, like, we exceeded some time. So there is a small trick there in the proof to lift the directional derivative to the gradient, okay? So in the gradient penalty, so GP proof we are trying to complete. And what it says is that infimum of pi in coming from joint probability distribution P R PG in the notation of the paper itself now. So I can write this as expectation, or I write this as Cx this and sum over all this, right? So it's the same thing. So here I will use the expectation notation x minus y. Obviously these are over the joint pi's. Okay, so then and x, y's are samples taken from the joint, obviously, okay? And so this is our Wasserstein distance, and then we said that there exists an optimal there exists f star that satisfies that is the solution of this, that is a solution of this, that is a solution of star, okay? And that f star is such that, okay, that f star is such that the gradient of f star is y minus xt by, which immediately implies that the norm of gradient of f star t is 1. Okay, and that was the reason why we had this gradient penalty. Here I'm using h, we can use f star also. Okay, and that's how we had this gradient penalty, because we are trying to help the optimizer, because the optimizer at the end is trying to find f star or h star in this notation, and that h star had a additional property, then just put it there so that the optimizer finds it useful. And in the proof, what we did is we proved the directional derivative part. Okay, so let me go to the last line of the proof that we had. So last line of the proof was del by del v of f star xt is 1. So this notation says that the directional derivative of f star xt in the direction of, we talk about directional derivative because in a high dimensional problem you can only talk about you can talk about gradients in certain directions. So this is my plane xy domain. So I say, okay, in this direction tell me whether my function is increasing or not. Okay, that's the intuition behind directional derivative. So, and this v was arbitrary, right? So this v was arbitrary. So, and we have said that in an arbitrary v direction the directional derivative is 1. Now we have to lift it to the gradient. So when we lift it to the gradient, now gradient and directional derivative are related, right? Because directional derivative along this is same as, is like taking gradient of f star and inner product with v. Okay, so these are the things that you recall from calculus. Now what we are saying is del by del v of f star is 1, and we are supposed to conclude that grad f star norm is 1. Okay, so let us try to prove this. Okay, so what we have so far is what we also have is these f stars are 1 ellipses. Okay, that was part of the theorem as well, because obviously ki duality tells me that, okay, f star, I think yeah, I mean I have written this, but this f star corresponds to the, this is equivalent to the supremum of f less than equal to 1. Okay, so this f star corresponds to the solution of this, which are equivalent by ki duality, right? So, and we know that if it is a solution, then obviously it's 1 ellipsis. So meaning that the gradient of f star is less than equal to 1. So since f star is 1 ellipsis, this implies norm of gradient of is less than equal to 1. So okay, so at some point xt, right? So what we have is that we can start from this. So 1 greater than equal to gradient of f star xt. Okay, we can also take a square because both sides are positive, so square doesn't change the inequality. And now remember that the result that we have is for directional derivative being 1, meaning this guy is 1. Okay, grad square grad f star projected on v, or the inner product with v, is 1. Okay, so gradient, you could see this as some generic vector, and it gets projected, and then it gives you the increment in the function along that v. Okay, so we want to bring that guy. So what we can do is add and subtract that term. Okay, and then see what happens, because we are supposed to use the directional derivative being 1. So if we do that, then it is easy to now write like this. Okay, so I have done a trick here that I have added and subtracted and splitted things out. It's very easy to verify back, because if I use this a minus b whole norm formula, then this gives me, just focus here. So with this, I do a quick verification that this is correct. So a square plus b square minus 2 inner product of grad f star xt and v grad f star xt v inner product close. Okay, so this is only for this guy. Okay, we are trying to verify that, and then once I add this, I should get back this, right? This is what we are trying to prove. And v is a unit vector, okay, because we took directional derivative in the, okay, so that's also known. So obviously, like, this guy comes out because this is a scalar. Again, I'm missing this. Okay, so this is a scalar because after taking inner product, it becomes a number. So this number can come out, and this will be norm of v square, which is 1. So this is, so after it comes out, it becomes a mod. And this is norm of v square, but this becomes 1 minus. Okay, this is interesting. Obviously, this guy comes out, the inner product, because inner product, what we know is alpha y is alpha xy, and this is a number for us. Okay, so this guy comes out. Okay, so I think we are missing again this here, right? So this comes out. So this is minus 2 of v grad f star xt, and then inner one is grad f star let us use this then xt. So this came out and this remained with this, right? Now these guys are the same, right? This is like x transpose y and y transpose x, but both are same. So this becomes a square of this. So I'm left with minus of one of these, because this became a square, but this is two of these guy. So minus that, and then we minus 1, and then there was an extra one of this guy here. So that gets cancelled, and what I'm left with is just this guy. Okay, so we can wrap this up. So this is, why do I put star here? Star should be on F. Now this and this, so this became minus of one of these. So, and this is a square, so like mod is not required now because this already is squared. So this is V . So this is one of these guy here and one of these guy here, they get cancelled. Okay, so this guy here and this guy here, they get cancelled, and what you are left with is this, which was your original thing, right? So this is valid. Okay, that's what I'm trying to say. And directional derivatives we have proved. So this is directional derivative on V, this is directional derivative on V. So these guys kind of become 1. Okay, so now let us try to continue from here. Okay, of course now you don't have to cancel this. So this plus this term, that's where we start from now. Okay, so we can write this again in clean way. And this we wrote it as Okay, we just wrote it cleanly. So this is, so we agree on this, and now this guy is nothing but directional derivative by definition. Okay, directional derivative is a projection of the gradient on that direction. Okay, so that's the definition. So this is del by del v of f star xt. Yeah, just use a mod so that, but anyway everything is a square, so it doesn't make it anything any problematic stuff here. So, and then I have grad f star xt minus v, and this is the directional derivative del by del v f star xt. So these guys must be 1. Okay, that's what we proved, right, in the last class. So this was 1. So this is the last class, and this guy is also 1. So this is 1 plus norm of gradient of f star xt minus v, because this is 1 now, and this is certainly greater than or equal to 1, because this guy is greater than or equal to 0. So this is greater than or equal to 1. We started with something less than or equal to 1, and we ended up proving greater than or equal to 1. This inequality must be an equality. In other words, this must be equal to 1 itself, because I started with 1 and we are saying 1 greater than or equal to 1, but we know it's equal. So the only possibility is that this must be equal to 1. Okay. So hence inequality, let us say this is we have used star already, right? So this is, let us say, inequality 1. Hence inequality I1 must be an equality so that means that grad norm term will be 0. Okay, so this implies norm of grad f star xt minus v. Now norms are 0 when the term itself is 0, right? So this implies grad f star xt is v, and the v that which we have started with was of the form, if you recall from the last class. So recall from the last class that v was y minus xt by norm of y minus xt. So hence what we have proved here is that this implies grad f star xt is y minus xt, and so we have proved a specific form, but then obviously one thing is clear, that norm of grad f star xt is norm of this guy. So norm of this guy is norm by norm of the norm is norm itself, so hence it becomes 1. Okay, so that's the proof of the gradient penalty, and this is where we leave the WGAN and the improvement. But what we will do now is to go to optimal transport, where from there we will extract one more generative model via direct estimation of the WGAN objective. Okay, so we go to something called optimal transport. So let us define what is an optimal transport problem. So let's define first the notations. So x, p, y, q be some finite probability spaces with, so it's finite, so let us say cardinality of x is n and cardinality of y is m. Okay, P and Q are distributions, and so we can look for, as usual, we have already seen this notation PQ is a collection of distributions on the product x, Cartesian product x y with marginals P and Q. Okay, so P is on x and Q is on y. Now consider the cost. Consider a cost C that goes from xy to r plus. Then the optimal transport problem is optimal transport problem is defined as, it's an optimization problem basically. DC is the distance between P and Q, which are distributions here, minimize over the joint PQ, and inner product of C with pi. Okay, and if we write it in the discretized form, then this is pi over set of all PQ and sum over xy C xy pi xy. So let us call this A. So this is a generic cost function, and Wasserstein distance is a special case of this. So example, if x, y are subset of Rn and cost xy is defined to be norm of x minus y, then the optimal transport between P and Q, then optimal transport between P and Q is defined to be dc PQ is minimum over pi distributions with marginals P and Q, sum of norm x minus y pi xy. Okay, and this is nothing but W1 PQ, which is the Wasserstein's distance between P and Q. Okay, so we optimal transport is a generic problem, okay, with generic cost function that you can define depending on the problem at hand. And if we are in discrete setting, then obviously the marginals are basically the sum over, so if I am computing marginal over x, then it would be sum of the joint for all yi. So the I equals 1 to, let us say there were m points in the y, so that's why we do it. And then if I have to compute the marginal with so this could be written in a compact form as pi 1 m. Okay, so we write this as pi 1 m, where this is like vector of all ones. Okay, so some of vectors could be written as vector dotted with the vector of all ones. That's what we did, right? So this could be seen as a vector x fixed, then this is a vector for x fixed, this is a vector pi x y1, pi x y2, pi x ym, and we are doing a sum of this. Then this is same as saying that I multiply this vector, so ideally I should do a transpose, and then vector of all ones. So this is nothing but pi 1m notation that we use. Okay, so this will be a dot product. So that's a small dot product notation that we use, and then similarly we can have qy. So qy will be sum of pi xiy and I equal 1 to n, and this we can write this as 1n transpose pi. Okay, these are shorthand notations for p and q. So in the discrete setting, we know that joint distributions are given by, so we have seen this in the probability, I guess. So we are given PMF values like this. Okay, so if these are my x values and these are my y values, so we can have something like that. So these are my x values which takes value 0, 1, 2. These are my y values which takes value 0, 1, 2, 3, something like that. So you get a tabular data basically. Okay, so p corresponds to your x. Okay, so if I have to compute the probability values for x, then the marginal with p, let us say this is x1 value, right? The marginal, I will do a y sum. So these are my y values. So px2, px3, this is what we are doing. Okay, we got marginal with x. So this gives me a distribution px whose values at x1 are px1, which is the row sum, column sum. And similarly, we do it for marginals when we compute y, then we are looking for these values. So this is q y1, q y2, q y3, and so on, right? Then I get marginals like that, q y1, y2, q y3. Okay, so this is something we recall from the probability class, and we have written just those row and column sums like that. Okay, so so we can now write these constraints as row and sum constraints. Okay, so we can simplify this this equation A. So let us simplify that. So this becomes dCpq Okay. So at least in the discrete case where we take a sum, right? If you have to do a continuous variant of this, then you have to write the integral. Okay, so integral with y and integral with x, and this will be an integral. Okay, so but usually we work with discrete. So even if it's continuous, we can make it discrete in some cases. Okay, so this is a discrete variant of the optimal transport problem, and it actually appears in many problems. Okay, many problems can be formulated like this, but we are not going into the optimization modeling and so on right now. Our focus is generative modeling, so we want to see how it helps in generative modeling. Okay, as I said, remark, this is a discrete Wasserstein distance. And it could be seen as mini batch approximation of W distance, the continuous one, between two continuous distributions. So essentially, if I can sample from some continuous distributions, I will get n samples of x corresponding to p, n samples of y corresponding to q, and then we can do that approximation, right? So more concretely, if p and q P Q continuous distribution, then sample x1, x2, xn that follows P, and y1, y2, ym that follows Q. So once you sample, you make them a PMF, essentially make a histogram of that, right? So you can define these distributions because samples by themselves don't approximate the distribution, right? So there was a question in the mid-sem, right? So you are supposed to pick numbers from 0, 1 to 9. The numbers were the samples, but then you say how many times it appeared, right? And that's the probability, and the probability of that, right? So you divide by the total number of cases and so on, right? So from samples we can create a distribution, right? So that can be created by, let's say, the histogram approach, which is 1 over n, and sum of 1 xi is x. So basically you count how many places x appeared for the given x. You count how many times it appeared, okay? How many of the xi's were the x divided by the number of samples. That gives you probability for x, okay? That's how we create distribution here, right? Basically we are creating PMF based on the samples, right? And then q tilde y, same thing. Now you have 1 yi is y. Okay. So given all the P and Q are continuous distributions, we can sample some points from there. We can sample some points from there, create a you can say it's kind of an approximate PMF based on the samples, PMF based on the y samples, and then you may wonder WPQ, which is the continuous distance between P and Q for the continuous case. If the samples are like good enough, then it will be approximately equal to WP tilde Q tilde. Okay. So we expect that WPQ approximates WP tilde Q tilde. Okay. So the underlying distribution could be continuous. Many things may follow continuous distribution, right? So we don't have to have purely continuous model. We can always, because end of the day, even if the underlying distribution is continuous, the samples you will be getting will be handful of them. Okay, so it's like n of them. Okay, m of them. That's it. So usually you will work with discrete number of samples. So okay, so the optimization problem we have, which is here, is, yeah, this is exactly the equation number that I have. I'm just trying to track this. So this was D. So the problem D is a linear program because it's a equality constraint, and this is linear. Okay. So because I can write this as C transpose pi. Pi is a vector, C is a vector, C transpose pi. So it's a linear program. Okay. So linear programming. So standard form of linear program, if you have not seen optimization method, then recall LP. Then LPs are of the form C transpose X, minimize over X, and let's say AX less than equal to B. So you can have this is a standard form of linear program, and people have studied this linear program and they know a way to solve this. Of course, the way to solve this may not be a very good one depending on the problem at hand, and you may look for something which is more tractable. But for the moment, what we know is that D is a linear program. Okay, so D is a LP. So I leave this as a, I mean, this is evident, but just for your clarity, you just rewrite this in that form. Okay, so D is an LP. Quality constraints are also included there. Okay, so it can be we can use an linear programming solver, and there are quite a few of them. Linear programming is a very well studied problem. But even linear programming for this is not very straightforward. Okay, so that's when a key idea was proposed by okay, some good algorithmic idea, because if you see until here, this is a very old problem. Okay, optimal transport is a very old problem. Okay, 1950s or something like that. Okay, even before that, and the fact that it's a linear program and so on, even if it's continuous, which may not be very easily tractable, you can have like discrete approximations, which is a linear program. Okay, but then the community needed better solvers for this linear program. Okay, so that's when and the problem here is, in its current form, okay, it's a bit intractable, and what we will do is that we will do some regularization for this by some entropy. Okay, and that regularization is a very common practice, so we will see all this. But let me first write down the key idea. So key idea came from the regularization of this, entropy regularization they call it. Okay, and then it becomes much faster to solve this LP. Okay, so this is by Kuturi, 2013, and the paper is Sinkhorn distances light speed computation of, I mean, it's not light speed, but maybe the author got carried away that sometimes it happens that you come up with some ideas, then you write paper titles like that. Okay, so it says light speed computation of optimal transport. Okay, there is nothing to do with light speed or physics here. Okay, it's just that light speed can be replaced by a fast computation of optimal transport. Okay, so the main the key idea that Kuturi proposed, the French guy, here while working in Tokyo. Okay, then so here he came up with a tractable way, faster way, like the name suggests, and to do that he introduced some regularity term. Basically, you pose your problem into slightly different form, and in the limiting case of that problem, you end up solving this. Okay, but that other problem is easier to solve. Okay, that's very common practice in numerical maths and so on. You transform your problem into something tractable and then solve your original problem via that. Okay, so then we go to something called entropy regularized optimal transport, and then we will provide an algorithm to compute this. Once we have an easy algorithm to compute this, we will build a generative modeling based on that. So what he proposed is, so the exact statement is that he just changed the optimization problem there. So d lambda c pq is minimum over pi marginals pq, and c pi, so we can also write this in c transpose pi form, minus lambda h pi. Okay, So he added a term which is minus lambda h pi, and obviously from there I see that if I solve this problem and if I take lambda to be 0, it approximates the original problem. Okay. So this is a different problem, it seems to be different, but for lambda 0 it's the same. So I can have an approximation to this via lambda going to 0 for that. Okay. So that's an idea. Now why would one add this additional term, right? Sometimes you add this additional term to make things tractable. In this case, the entropy function is in fact a strongly convex. Combined with the linear, it keeps it strongly convex. Strongly convex, existence of minimizer is there. Okay. So strongly convex, existence of minimizer is guaranteed, and that helps in the problem. Okay. So strongly convex minimizer is there. That's what he's trying to do. Okay. So yeah. So clearly as lambda tends to 0, obviously this term is going to 0, and this becomes an optimal original problem. So we have put a lambda here to distinguish that this is entropy regularized OT problem, right? So this is, we have d lambda CPQ goes to dc PQ, okay, which is dc PQ is the original equation D loss. Okay. And this I believe we should make it F. Okay, I'm missing some numbers, but this is an important one, so let us keep it F. And this is what we are going to solve. So in this class we will build a solution for entropy regularized OT, which gives me faster way to compute W loss, which gives me a very straight idea to build a generative model. Okay, so one of the link is also that this problem F can also be written in terms of KL divergence. Okay, and with a proper choice of P. So let us try to do that. So reframe equation F as a KL divergence term with suitable choice of the probabilities. So define, so for this, okay, so for this what we will do is we will define few things. Okay, so let us say we define k xy, which is exponential of minus c xy divided by lambda. Okay, so let us define a function k xy which is like this, exponential of minus c xy, lambda all are known. So we have this valid definition of k xy, and let us define z lambda to be sum of these k xy over xy. And now what we will do is that we will normalize this k xy, and after normalizing this it will behave like a distribution because the values will be between 0 and, because we have in the denominator we have summed up. Okay, so it will be values between 0 and 1, and the total sum will be 1. So any vector, if I define like that, the individual entries are between 0 and 1 and the sum is 1, that by nature defines a PMF, probability distribution. So a trick here being done is that introduce a scaling factor which is nothing but the sum of these. So basically normalize this, so this divided by this will define a distribution. Okay, that's how distribution, for distribution that's what you need, that's all. Okay, the entries must be greater than 0 and sum will be 1. So this is the thing that we are going to do, and with that, why we are doing that? We are doing that because we want to see this as scale divergence of some transform probability distributions. Okay, but this transform probability distributions is also fetching data from the original problem, which is C, lambda, and all those. Okay, so and xy's are obviously sampled from pi, so pi role of pi is also there. Okay, so okay, so as I said, according to our plan, we will divide k by z lambda and make a distribution out of that. So so then 1 by z lambda kxy defines, so in the literature there is a name for this, it's called Gibbs distribution. Okay, so defines a and let us call this distribution P lambda k. K stands for that k. Now with this choice of our P, if we look into the KL divergence of the pi joint and the joint that we computed like this, the Gibbs distribution, so-called Gibbs distribution, it turns out that this will be very similar to the, very close to the DC loss. So we have d pi p lambda k, which is sum of, so this is d, d is obviously like the KL divergence, right? This is the standard notation we use. So we introduce the notation of KL divergence. So this is like pi log pi by p lambda k. Okay, so and this is a expectations, it will be sum over all xy. So this is pi xy log of pi xy by k xy, and it was divided by z lambda, so I put z lambda here. Okay, so this is the KL loss between pi and p lambda k. P lambda k was defined this. This is our p lambda k, which went there basically here. Okay, so this is p lambda k, and now we want to know how it is related to d lambda c. Okay, so let us work on this. So this is what do we have now? So we have this sum. So we are supposed to, we have to keep an eye on f, and we have to see how many terms of f we can retrieve. Okay, so for instance, do I see c pi? Okay, so do I see all those terms? And h lambda, h pi is, if you remember, h pi is the entropy. So h pi entropy is like x log x. Okay, so that's how the entropy looks like. Okay, so we will try to derive everything as much as possible from f. Okay, so let us break this log. So this goes with this, and minus of this with this, and then we can have this log term separately for this. So plus log of z lambda, because it's in the product of the log. Okay, so this is whole thing. Okay, so let us do that. So this is sum of pi xy log of pi xy minus sum of pi xy and k has been used now. So k will be exponential, and then somehow the minus log kxy, then the log and exponential gets cancelled. So then I will get c. Okay, so I will explain this first. Let me write down. So minus c xy by lambda, and plus the final term with z lambda. So this is this will come with the log z lambda. Okay, so we have just expanded this term, right? So pi xy log pi xy minus sum of pi xy log kxy, but log kxy, k was exponential of minus cxy by lambda. So log or exponential got cancelled, so I just got minus cxy by lambda. So that term is also clear. And then the third term is pi xy log z lambda, pi xy log z lambda. Okay. Now from here we have to see, we have to keep track on f, what are the things we have in hand and so on. Okay. This is looking like the entropy term, right? Entropy terms are like that, x log x. So this is the entropy, right? So this will be nothing but h pi form. Okay. So let us keep track of these things. So this will be, in fact, the entropy is defined to be minus x log x. So then this happens to be the plus. So this will be minus h pi. Okay. So let us track these terms here. So this is minus h pi. Now the second term is exactly of the form c transpose pi. Okay. So c inner product with pi, and 1 by lambda plus 1 by lambda comes out. So this term is this term is 1 by lambda inner product of c with pi. So we saw that c inner product with pi is coming, minus h pi I see already, and then we are left with the last term. The last term is sum on xy, but z has nothing to do with xy, because z is sum of k over all xy. Okay. So this will come out, log z will come out, and then because it's already a summed form of all xy, so it's nothing to do after the sum anyway for z lambda. So it comes out, and this being a PDF, the sum of PDF must be 1. Okay. So hence this term becomes equal to log z lambda, just log z lambda, and this guy sums up to 1. So we can say that this being a PDF, joint PDF, sum of joint PDF is 1. Log z lambda comes out because it's already summed up, so summing up again doesn't make sense. So it becomes a constant of xy after the sum, so it comes out of the sum. That's it. Okay. So these are the terms we have. So now equation f, which is d lambda c, now reduces to in terms of, I mean the KL divergence is now related to d lambda c with some additional log terms and so on. Okay. All right. So what we have now is d pi p lambda k is 1 by lambda c pi minus h pi plus log of z lambda. Okay. So this is what we have proved. And so if we look into the arg min, z has nothing to do with that. Okay. Because if I look at the distribution pi, then minimizing this KL divergence is same as minimizing the DC. Okay. So this implies arg min over pi, where pi is pq, c pi minus lambda h pi. So here by arg min we mean the pi, this is the optimization problem in pi. unknowns are pi. So the minimization over pi is same as minimization over this, okay, because 1 by lambda constant can be taken out and lambda goes with h pi. So this is exactly the same, okay. So this is argmin of pi in pi pq q lambda k, okay. So I hope you understood that the minimizing, because lambda 1 by lambda k if you take out, then this will be c pi minus lambda and plus lambda, but then constant doesn't play a role in the minimizer, so 1 by lambda can be taken out. Also pi has nothing to do here, so essentially it's same as this, okay. So what we have seen is that the entropy regularized optimal transport loss is same as minimizing the KL divergence loss with p given like that, okay. P is created as a Gibbs distribution, okay. So okay, so essentially we can work with this loss, okay. Now what is now our focus goes to solvers, okay. So solvers for, so what is the solution of this optimization problem, right? So most problems that we encounter are follow two stages. First stage is modeling, okay. By modeling I mean maths modeling, okay, not the other types, okay. So this is the optimization model. Usually most problems are like that, and then solver for the optimization problem. Almost all the problems that we encounter in our daily life are nothing but some minimization maximization problem, and this also is an important step. In fact, this is an application oriented guy must understand this, how to model a problem, okay. Given arbitrary problem, how do I see this as optimization problem, and then once I have an optimization problem, what is a good solver for that, okay. Because solver, arbitrary solver one can use, but then it won't be tractable. People won't use your model because the solver you provided are very bad for the model, okay. So these are the two key things you have to keep in mind, okay, as a researcher. How you model your problem, someone gives you a problem, and for that model are you coming up with a good tractable solution, okay. So leaving it until here also is not a solution to our problem, okay. So what is a good algorithm that can find an optimal pi, okay, also needs some work, okay. So solver for, so let us say we call this, I didn't use okay, I don't use any equation for this, so let us say this is double star. So we will now go into a solver, but then when I look into these problems, optimization problems like this, then a usual question is this a tractable problem? Do you guarantee existence of solutions, okay. So the typical questions that you may ask is, does a solution exist? So these are called existence problem. And then second question sometimes people ask is the solution unique? So this is called uniqueness. What is interesting is that for many problems you can answer both this without actually telling the solution, the method to arrive at the solution itself, okay. So I may prove the existence of solution, but I may not tell you how. So there are proofs where you just say that existence is there, but it's not a constructive way to give you a solution. You have to find out, okay. So and similarly we can say something about uniqueness. without actually telling you how the solution came. So how do we guarantee such things? That requires a bit of additional stuff which is not part of this course, but in the passing I will just tell you what people look for. Okay, and as I said, that will go a little bit in a different direction, but then I will just tell you what people usually do, and in fact this is what they write in their papers. Okay, so but we won't go in. All right, so this problem that we see here, double star, is an optimization problem posed on this space, where this is a space of distributions. Okay, space of all distributions. Okay, now when is the minimizer possible? Okay, I mean, when is the existence guaranteed? In this case we are trying to find minimization problem. Okay, so one of the results that we have is that borrows things from metric space, calculus, topology, and so on, are some of the basic things. For instance, fact a continuous function on a compact space attains extremum. Okay, so that's one of the results that borrows from metric space and so on, analysis, real analysis basically from maths. And so to guarantee an existence of a solution here, what we are looking for is the space where I'm looking for, is it compact? Okay, for instance these guys. Okay, so there are like known results on this. So space of distributions compact. Okay, so claims are like this. Is a compact space. Okay, now what is a compact space? But before I tell a little bit about these things, what we need I will just write down. Okay, claim 2 is the negative of the entropy is strongly convex. So these are the two ingredients that you need to provide a guarantee of solution of double star. Okay, but as I said, these two claims themselves rely on concepts like compact space that you may not see. Okay, and strongly convex. If I have to do strongly convex, then it's the easiest thing to show that the negative of the entropy is strongly convex. So that proof can be done because essentially it's saying that the functions of the form x log x is strongly convex. Okay, so that's what it means. Okay, so let me kind of like just tell you in the as some remarks, and then you can okay, yeah, so let me prove this claim. So claim 2, proof of claim 2. So for this what you need is definition of strongly convex, and this you know, and you just say that I know the strongly convex definition and then I can prove it. Okay, so this is like 4 or 5 lines, that's it. So it's not a big deal. So this claim is that this is strongly convex. So we have minus h pi is pi log pi. We are saying that this is strongly convex, right? So and then okay, first thing is like let me define what is strongly convex, and then I will go ahead and prove. So first of all, recall strongly convex. So a function is strongly convex, a function f is strongly convex if the double derivative of f, assume that it's differentiable also. So double derivative f is greater than or equal to mu times identity. Okay, so basically double derivative will be the Hessian of f. So this means that same as lambda min of the Hessian of f is greater than or equal to mu. So the minimum eigenvalue of the Hessian of f is guaranteed to be greater than or equal to mu, and mu is positive. Okay. So then f is called, then f is mu strongly convex. Okay. So this is the definition of strongly convex. Very simple. Take double derivative of f and check that if its eigenvalue is greater than or equal to mu. Okay. Then so if you can ensure that the double derivative is greater than or equal to mu, then it's strongly convex. Now can we say that this is strongly convex? This is of the form pi log pi. So essentially you have to take double derivative of pi log pi and say that it's greater than 0, okay, with some choice of mu. Okay, so let us do that. H pi minus h pi is pi log pi, and we could write this as a sum, but as I said, each sum individually, if it's strongly convex, it's fine. Okay, because if each terms are individually strongly convex, the sum will be also individually will be together strongly convex. Okay, so that's why it's enough that I just look at pi log pi. So then d by d pi of minus h pi is first function differentiation of the second plus second differentiation of the first. So this is 1 plus log pi, and then d2 by d pi square of minus h pi is 1 by pi. Okay. Now pi being a joint PDF, the values are greater than 0, okay, and less than 1. So pi xy values being probability values, it lies between 0 and 1. So pi xy values lies between 0 and 1. So this does imply that this is greater than, I mean, this does for sure imply that this is greater than 0. But what it also tells me is that choose any, because 1 by pi is greater than 0, but then 1 by pi is greater than, in fact, 1. Okay, because pi lies between 0 and 1, since pi lies between 0 and 1, 1 by pi is in fact greater than 1. So choose mu, any mu less than 1, then minus h lambda is strongly convex, is mu strongly convex. Okay. So what we have proved just now is that negative entropy is a strongly convex. Now why are we doing this? Because if we have done this regularization for some reason, right? So we have done this because we know that it's a convex regularizer, and combined with a linear, it still makes it convex, strongly convex, because linear has no role. Because if you combine both c pi minus lambda h nu, then you will see that if you take double derivative of the c pi, it's a linear in pi, so second derivative just goes away. So everything depends on lambda h pi. Okay. So lambda h pi being strongly convex, overall c pi minus lambda h mu is strongly convex. And if it's a strongly convex, it has a unique minimizer, and the minimizer is guaranteed because the space of the distributions is compact. Okay. If you are looking for a minimizer in a compact space, I did not tell you what is compact space. I will quickly write down. okay, but these are the arguments needed. So the first claim that I wanted, as you can see, is very easy. I told you what is strongly convex, and I proved that it is, and in fact I proved that it is a convex regularizer, which is a very common practice to solve an intractable problem. I put a convex regularizer, and then the solution is guaranteed numerically, it will converge and so on. Claim 1, okay, is a compact space is a little bit difficult, and I will not be able to do this because it will require some concepts from measure theory, which will be will take a lot of time, because there is a additional thing going on here. So first thing is, like, I mean, these are not just distributions, okay, these are distributions with marginals in P. So if I have a space of distributions pi which are compact, then the space of distributions with marginals P and Q forms a closed subspace, and closed subspace of a compact space is compact, okay. So if pi, the space of all joint distributions, okay, I am doing this very quickly, these things will not be part of the course as such, but I am just trying to put these things in one place, okay. Space of all distributions is compact, and given that the space over which this is defined, xy, is compact, okay, I will quickly define compact later on, but so if this defined is compact, then pi, the space of distributions with the restrictions that the marginals are P and Q, is a closed subset of pi. So can we prove this? Okay, I'm writing down this as a sketch for those who take interest in real analysis. So I'm not going in detail, obviously, but so closed subspace of a compact space is compact. So this implies that the P pi Q is compact. So as I said, if I am minimizing a function or maximizing a function on a compact set, then the minima or maxima is guaranteed, okay. That's the reason why we are looking at compact, and obviously we are not going into the proof of this, okay, but the whole point is to point out that the minimization problem we are solving, the fact that we did convex regularizer, being a strongly convex, unique minimizer is guaranteed, minimizer is guaranteed, and unique minimizer is guaranteed. So that's what we have. That's where I will kind of. And another thing is, convex implies continuity, okay. So strongly convex, if you want to extend further, so strongly convex implies continuity. Continuous function on a compact set attains maxima or minima. So that fills the full picture, okay. So let me write down these additional steps. So convex, or in particular strongly convex, now you have the full picture that continuous function on a compact space attains, in this case we are looking for minima. It will attain both maxima or minima. In fact, I can extend further on this, that the reason why it happens is that if f is continuous and f goes from x to y, then f of x is compact. F of x is compact. This also means that fx is closed and bounded. Okay, and all this guarantees you the existence of minima and so on. Okay, and then being a strongly convex implies uniqueness. So strong convexity, again I am not doing these proofs, implies uniqueness of solution. Okay. So these are the things they put this in their papers, Sinkhorn generative modeling paper, where they put this small details, and that's how the paper looks good, well thought out, things like that. So this part that I wrote, it may be a little bit off for some of you because you may not have seen compactness and the results like strongly convex implies uniqueness and so on. But we now come back to our problem, okay, because this goes in the area of matrix space real analysis or topology, okay, where these things are discussed in detail. So this is not required in this course, but if you want you can, but you should know these facts that I have written without proof. Okay, and this I will put as an exercise. This is simple thing to do. Okay, so this will be your exercise. This will be also be an exercise. Okay, you can try this exercise, like you can have a look at the definition of a compact set, which is not very difficult, and with this you can try some of these. As I said, like proving this is not easy. Okay, I mean these things require some concepts from measure theory, so that you can skip, but other things you can. Okay, so coming back to our problem is that we had an optimal transport problem. We did a convex regularizer. Convex regularizer, given that this is compact space, this convex regularizer made this whole thing convex, strongly convex. Okay, because H pi was strongly convex, and the first term being linear plus strongly convex is strongly convex. So that's guaranteed that whole thing was strongly convex. Unique minimizer, existence of minimizer, everything is done. Now the only thing I don't tell you is that all this, as I said, existence and uniqueness follows from topological arguments, continuity, convexity, and so on, but it does not kind of tell you a way to find the solution. So far I know that there is a solution and it's unique. Now let us now look into possible algorithm to solve this. Okay, so so now going back to our original problem, yeah, so we were so we are now supposed to find an algorithm for solving f basically, but f was transformed into the KL divergence, which I have replaced it. So let us go back to the algorithm now. Just as an additional remark, minus, no, so this being linear, C, yeah, I mean C pi being linear minus lambda H pi being strongly convex, minimizers being strongly convex, dc lambda pq, oh, so C pi minus lambda H pi is strongly convex. It remains strongly convex. Okay, so we are done with the existence of. So in conclusion, F has existence of solution and solution is unique. Okay, now now we want to go to the algorithm, and our optimization problem is argmin pi from pi pq d pi p lambda k. So this is our optimization problem. Okay, this is our optimization problem. We converted the f problem to the k divergence, and now we are supposed to do the minimization here. So now it's about algorithm. So so what we observe is, let pi p and pi q denote row and column marginal constraints. So we use a notation here, row and column marginal constraints. So basically this denote distributions with marginals p and marginal q. All distributions with marginal p, all distributions marginal q, and but what we are looking for is the one with marginals p and along y marginal q. So essentially pi pq will be an intersection of pi p and pi q. So this implies pi pq, which is a distribution which has one more restriction, that summing over y will be p and summing over x will be q. Okay, but these guys have summing over y is p, but we don't say about other way. Okay, summing over y may not be q. So this is a bigger set than this. Similarly, this is a bigger set than this. It includes one. It also includes one with marginal p. So what we are trying to say is that pi pq is the one that is an intersection of this. Okay, so what we are looking for is an intersection. Now pi p and pi q are affine sets. Why they are affine sets? Because they define a set of all functions whose sum is 1. So that's an affine constraint. So it's an affine set basically. So we have defined this set before. So these are affine sets, and we are looking for solution that intersects these affine sets. So basically I have some affine set. And what I am looking for is some intersection between these. So the intersection point between these affine sets will be these guys. Okay. So now the problem from algorithm point of view is, how do you find intersection point of two convex sets? Okay. What is an algorithm to find intersection point of two convex sets? That's a very generic algorithm that we are trying to solve here. Okay. So is it feasible? How it could be done? Okay. So let us look into this now. Okay. So basically we are into algorithm, which usually is not much left, I would say, but I will complete it today. So then next class we are supposed to start VAE, variational autoencoder. Then we go to hierarchical variational autoencoder, variational diffusion model, and then we go to score based diffusion models. That's where you get into DALI and all those. And then final 3-4 lectures will be transformer based model, language models, and so on. Okay, so let us complete this sinkhorn based generative modeling. So we are left with an algorithm for this, because if I know an algorithm to do this, I'm done, because that essentially tells me that I can compare two distributions in a tractable way, and that acts like a cost, and I can update the parameters of my network and minimize the cost. So this is where we are. We are supposed to find an intersection. Okay. We are supposed to find a pi which intersects this pi p and pi q. This could be done by an idea called alternating projection. Okay. So alternating projection idea is can be explained in this way. So alternating projection is so this is my convex set C1, this is my convex set C2, and the alternating projection idea says that you start with some point in C1 or C2 and you find the distance closest to C1. Once you reach C1, from C1 you find the distance closest to C2, and then from C2 you find the distance closest to. So if you follow this process, you will get to an intersection point. So for instance, let us say by my random choice I was away from the intersection. So this is, let us say, my point x1. Then I find the point that is closest to the convex set, so which will be this guy, and I get a point y1 in C1. From y1 I will find a point that is closest to the convex set C2. So this is this, which is x2, and from x2 I will find a point which is closest to C1, and as you can see, this way I will arrive at an intersection point somewhere. Okay. So this will be x star, this will be y star. So basically they will match at some point. So this is the basic idea of alternating projection. It's a very simple idea, and it works for sets C1 and C2 being convex. Okay. And this is what we are trying to do here. We will start with some solution, let's say P, okay, and then we will keep iterating between these, and eventually we will get to some joint distributions which are in there. Okay. And so I will write down this algorithm. So this alternating projection idea is, as you can see, it's very simple. So start with x node in C, then so let us say this is C, and let us say this is D, and this is, let us say, x node. Okay. Then alternately project onto C and D. Then yk is PD xk, and then xk plus 1 is projection of yk, and so on. So we can keep doing this. Okay. So yk is a projection of xk. From xk I go to the D, then I go to yk. Using yk I go to the C, then I get xk plus 1. So I keep doing this. It's a very simple idea. So this was proposed by Chene and Goldstein in 1959. The paper is Proximity Maps for Convex Sets. For convex sets. Okay. So this is a simple idea. So the fact is that if C intersection D is not empty, meaning they do intersect, then sequences xk and yk both converge to a point x star in C intersection D. So that's the alternating projection idea, and we want to apply it here. So let us now try to write the algorithm then. So this is right. So according to this, the algorithm is easy now. So here we are looking at some distance, right? Some distance measure. We are saying that from x naught, look for the y which is closest on the other set, and that distance in our case is the KL distance, KL divergence distance. Okay, so if we use this alternating projection idea, then what it says is that initialize pi lambda, which is p lambda k, and define alternating projections pi L plus 1 lambda is arg min of d pi lambda L if L is even, and this is pi in pi p, and arg min of pi in pi q, and this is for d pi when pi L plus 1 lambda for L odd. So this is the projection that we want to do. Okay, so in the first step, we have taken some pi naught lambda as an iterate, and then we are looking for the closest to pi p. So in this case, if you want to see these sets, then you can see these as pi p here, and these are the set pi q. Okay, so this is your pi naught lambda, and you are looking for the smallest possible distance in pi p. Okay, smallest possible distance pi p. Then you got some. So this you can see as even iterates are from here. So these are even iterates, and these are odd iterates. So you got this pi lambda 1. Now from the pi lambda 1, you find the distance in q. So you got this, then you got pi lambda 0 1, and this is 2. Then you do like this. Okay, the only thing is that your distance now is this KL divergence. Okay, but it can be any good distance. Okay, so this is the alternating projection idea, and obviously, like you can say that for the algorithm, I want to know what is this, right? Because I have to take the distance. So once I start with this, how do I know this? To know this, I need to solve this optimization problem, right? Okay, so let us try to fill this gap. So okay, so first thing to note is that pi p, which is set of all pi such that pi 1m is p, so row sum is p, and then pi q is set of all pi such that x was y was m, x was n, right? So this is n, is Q. So these are affine sets, okay, are affine set. So you do this as a simple exercise. Now these are affine sets. So this is 1 transpose pi here, set of all pi whose set of all vectors whose sum is some constant. So that's some affine set, right? So you can prove this explicitly. Now the fact that these are affine sets, this also implies that these are convex. So the alternating projection idea works there because affine sets are convex. So everything fits quite well. Hence pi p and pi q are convex because affine sets by definition are convex. And so now let us look into this minimization problem that we have, and that should give us the algorithm. So let us look into the even case. For L even, need to solve this problem. Arg min pi 1m is p and d of pi L lambda. So we are supposed to solve this minimization problem. Arg min constraint is that row sum is p, okay, and d of pi lambda L. Okay, so since this is a constraint, this is a constraint optimization problem. So we can build a Lagrangian of this. So we put the constraint with the Lagrange multiplier. So since this is a constraint problem, introduce Lagrange multiplier. In this case, let us say is f. So if you have a Lagrange multiplier, then the problem reduces to arg min and max over this. So pi f. So we are forming a dual form now. So pi L lambda plus f pi 1m minus p. It's equality constraint, doesn't matter, but yeah, let me write like this: p minus, because anyway it's 0, p minus pi 1m. So I have introduced a Lagrange multiplier. So dual I have discussed before. So this is a introduce a Lagrange multiplier. So this is now in dual form, where we have formed a Lagrangian. Lagrangian is infimized over pi, and then we maximize over the Lagrange multiplier. So now we assume a strong duality, then min and max can change. So interchanging min and max. So if we interchange min and max, then we have so if we interchange min and max, then first we look at the mean problem and look at the mean problem So if we look at the mean problem, then it is arg min of pi d of pi L lambda plus f p minus pi 1m. Okay, so we minimize. We look at the mean problem only right now. I flipped that because of the strong duality. Okay, so this is via Slater condition, right? Because yeah, so we have to say that d in one of the argument, let us say pi on the odd argument, it's convex. Okay, and I only have equality constraints. Okay, so Slater condition holds. Convex function plus only equality constraints. Okay, so hence we had strong duality. If we have strong duality, we have also seen in the previous class, then mean and max can interchange. And now we look into the mean problem. Now for this to minimize, the derivative must be 0 with respect to pi. Okay, so from first order optimality, so what we must have is del by del pi of this quantity must be 0 plus f must be 0, right? If something has to be minimized, then the gradient must become flat. So we take a gradient, first order gradient of this, and if we do that, so first of all we recall what was our d pi. Recall that d pi L lambda is sum over pi lambda L xy log of pi lambda xy divided by pi L xy. I mean, the way we have to write is a little bit more. So what we are essentially comparing is because our current pi, and we are comparing the distance between the old pi and the current pi. Okay, so this I can leave this as a formula, write this, because I don't. But what essentially we have now is pi is some successive pi that we have, because we are doing this iterations back and forth. So pi L plus 1, pi L plus 2, like that. So if I have pi L, then the distance that I'm supposed to compare is with pi L plus 1. Okay, so more precisely what is going on is that this pi that you see here is the successive pi. So let's say pi L plus 1. Okay, so if I replace pi by pi L plus 1, then I have a change here. So I will do that now. So but current pi is pi L plus 1 lambda f, and we put lambda f also just to highlight the fact that we have a Lagrange multiplier going on. Okay, so there is some dependency on f. So I'm introducing this sub f also. Okay, but that's fine. So so what we have is that when we are computing a derivative with pi, essentially pi is the successive pi, so it will be pi L plus 1 lambda, okay, or lambda f, it doesn't matter. So pi L plus 1, and with this, so we are essentially supposed to compute derivative of pi with d pi L plus 1 pi L. Okay, so what we are looking for is del by del pi L plus 1 lambda of d pi L plus 1 lambda of pi L lambda. Okay, so now we write down what this KL divergence between L plus 1 and L means, which is which the formula we know already. So this is del by del pi L plus 1 lambda, this is pi L plus 1 lambda xy log of pi L plus 1 lambda. So it remains with the log as the main argument. So this is pi L plus 1 lambda, and then minus pi L plus 1 lambda log of pi L lambda. Okay. So sometimes I write xy, sometimes I don't write xy, but there is xy all the time. Okay. So this is what KL divergence is between pi L plus 1 and pi L. So it's pi L plus 1 log pi L minus pi L plus 1 log pi L. Okay. So and we are supposed to compute a derivative with respect to pi L plus 1 lambda. So we have to look wherever where we have this pi L plus 1 lambda, we will take a derivative with that. So if we do that, we are almost there. Okay, so one more page is needed to get in fact we are not there as a full because but let's see. So the first set of solutions we have, so we have to take a derivative with this. Now if we take a derivative with this, what do we get, right? So let's see this. So these both the guys for which I am going to take the derivative, both the guys are there, right? So the product rule will apply here. Okay. So just in case this guy is looking a bit too much, so let me do this in a clear way, so that because this expression is little bit, yeah. So log of pi L plus 1 lambda xy minus pi L plus 1 lambda xy log pi L lambda xy. This is what we have written, and we are taking derivative with pi L plus 1 lambda. So if we have that, then we use the product rule. The first fraction and differentiation of the second, that gets cancelled, and we get a 1. So the first term is 1 plus second and differentiation of the first. So the second one remains. So this is like log of pi L plus 1 lambda xy. So we are done with this now. Minus, and this guy with which we are taking the derivative is only here, and this acts like a constant. So derivative of this will be just this. So this will be minus the constant, which is log of pi L lambda xy. Remember that we have done this part for the moment, where pi is our successive pi which is L plus 1. So we have done the derivative of the first term, but then we also need to do the derivative of the term with the f, and the first order optimality suggests that that this derivative will be 0. The first one is done. The second derivative with respect to the pi will be minus f. So derivative of this with pi will be minus f. Okay. So if I have to write down in full, so so this is our first part, and then the second part is and we have del by del pi L plus 1 lambda of this term, f term, f p minus pi L plus 1 lambda 1 m. We are supposed to take derivative of this, but pi L plus 1 lambda is only here. So this dot product with this, f dot product with f is a constant, p is a constant with respect to pi L plus 1. So that term derivative will be 0. So the only thing that is left is minus f transpose pi L plus 1 1 m, but that will be with respect to the pi, it will be just minus f. Okay, so that will be just minus f, and if we do it for some specific xy, okay, because if you see these terms pi is like a vector here, okay, xy, okay, and here also these are all vectors. The Lagrange multiplier are also a vector for as many of the components xy, okay. So so we can do this for a specific x, okay, if we like. So for instance, if I do it for a specific xy, okay, and for all xy this will be the same thing, but if I specifically for xy, then it will pick the x term specifically, okay. So for instance, if it is done for fixed xy, then what it will ideally, usually it will produce the vector f, but if I restrict to some xy, then it will just pick the component of f which corresponds to the x here, okay. So this will be for that fixed x, this is what I'm supposed to get. So and we can say the same thing for these guys as well. For a fixed xy, this is exactly what I'm supposed to get for that fixed xy, okay. So these are once I instantiate these things, then these are for fixed x and y, okay. So and this is minus because there is a minus sign here, so this is a minus. Okay, so we have this derivative term. Now this will be equation h. So we have g and h. Now we have to write the iterates then. Okay, so combining g and h, we have 1 plus log pi L plus 1 lambda xy minus log pi L xy lambda minus fx equals to 0. This is the first order optimality. First order optimality. Okay. And this first order optimality, and from here I will solve for the pi. Pi is the one I'm looking for, right? So I have to solve for what is my new pi L plus 1 in terms of the old pi, okay. So that's the iterative algorithm I'm looking for. So basically solve for pi L plus 1 lambda xy. So this gives me log of pi L plus 1 lambda xy, and if I do this, then minus 1 goes here, plus fx comes here, plus log of pi L lambda xy. So I'm trying to solve, and then log will be moved there, then we will have exponential term there. So this will be, this implies pi L plus 1 lambda xy is exponential of minus 1 plus fx, and log and exponential gets cancelled. So this is pi L lambda xy. So from here I can also write e, so which is e exponential of fx minus 1 is pi L plus 1 lambda xy divided by pi L lambda xy. Now while doing these iterations that we have where we get this pi L plus 1, we have to ensure that this pi L that we are getting is coming from the pi p and so on, okay. So with the marginals p, okay. So if I am getting here, then these are with marginals p. If I am getting here, these are with marginal p. So this is a fact that we know, okay, because the way we are doing projections is like that. So we will use this fact and see what else we have from there. So this gives us the primal problem. I mean, one of the possibilities, and there is a slight variation of this iterative rule, which is more simpler, which we may do in the next class. Okay. So but let us finish this algorithm first. So since pi L plus 1 lambda is in are the ones that goes to the marginal p. Okay, these are the kind of the odd ones. The odd ones, according to our case, pi l plus 1 are coming from here, let us say. So they are from the pi p. We have sum over lambda l plus 1 xy. Now, if you look into this sum and pi l plus 1 we have calculated from there. So we are going to substitute that. So let us say this is 3 stars. Okay. So so from 3 stars, then we have, and so we kind of like replace pi l plus 1 by e to the minus 1, so e to the fx minus 1. So if we do that, then we have fx minus 1 sum of pi l lambda xy y, because this is these are yeah, this this is marginal with y. Okay, this is we should so this is pi l plus 1 lambda is in pi p, meaning I should do the, if I do the marginal with y, I should get the marginal in p, marginal p. So this should give me the p. Okay. So in other words, like I should have started with this. So px, because px is lambda l plus 1 marginal with y, because they are the one from the set pi p, and we did that, and then from there, what do we get? From there we get that e fx minus 1, we solve for that. So this is px by sum of pi ly xy. So now we are supposed to do the final 2-3 lines basically. So so the even and odd kind of we are trying to track now. I mean, so if I have to do, let us say I use pi to l, then which is even iterations, then it is p by pi to l minus 1. Okay, that's fine. And then pi of yes, that's fine. Okay, basically e that I found there, I can substitute there. So e I can get rid of, then everything remains in pi. Okay, so if we substitute that e from here, then l plus 1 we can, the question is which one we take, even or odd, like that's our choice. It's a notation thing. So let us say I take e f x from there. Okay, so let us say we let us say this is equation x. Okay, so from x we have this. So we have pi l plus 1, which we will change this at 2l, 2l minus 1, odd, even, 2l and 2l plus 1. That's fine, but for the moment let us first write this xy by pi l lambda xy, and this is equal to px by sum of pi l y, I mean not y but lambda. This is not y, maybe this is what you were pointing. Yeah, so this is lambda, and these are over y. So basically we will now we want to write down for because the sum is there, so let us do this is with y. Okay, that's fine. So we will solve for pi l plus 1. So this guy will be sent there. Okay, so let us send it there. So this is, so hence pi this will be when it gets multiplied by this guy pi l lambda Okay. So now this is we have done is for pointwise x and y, but since it's a distribution, joint distribution, we have to specify this for all tabular data x and y. So we can vectorize this notation and use diagonal operators to make it write it compactly in some form. And another thing we can do is that since we are want to write odd even, so you can change L plus 1 to even to L, and this you can change L to 2L minus 1 to L minus 1. Just to, I mean, already we have this iteration, it does not matter whether it's L plus 1 will be, we will treat it as even, L as odd. So just for a notation thing, we can change this to 2L and 2L minus 1. Okay. So, and then we will vectorize. So now we are giving the distribution values for fixed x and y, but we can give it for all x and y. So hence, because it's independent, we can just write it for all x and y. Okay. So we can just vectorize these notations. So changing L to 2L just to make that look like it's even iteration, and so changing L plus 1 basically to 2L and L to 2L minus 1 to show that it is an odd iterations. Then we have pi to L lambda xy is px by sum over pi, L becomes 2L minus 1. So 2L minus 1 lambda xy, and this L becomes 2L minus 1, and this is point value on an xy. So this is still for some point x and y for which I am suggesting the probability, joint probability, but then we can vectorize this. So next step is to vectorize this. For all x and y. So if we do vectorize this, then we essentially make vectors and matrices. So this is like 2L lambda, this is, use a diag operator. Diag operator makes a vector into a diagonal. Okay. So this is P. Now P became a vector now. Okay, defined for x values. So it's as long as the length of x. So length of x was n, I guess. So this and then divided by pi to L minus 1 lambda 1m. So this sum that you see here is now, as we have also seen before, the sum over y. So y, there were like m points, so the sum can be written as a dot product with vector of all ones. So we do that, and px divided by pointwise divide by this guy and make a diagonal operator. So if you see row by row, then for x, y, this is the value you will get from here. Now we have made this into a vectors. Entry wise, you can get x, y values from here. Okay. So now I'm not writing x, y here for phi, because now it's a vector. Okay. In fact, it's a matrix now because it's a joint distribution of x and y. So pi's look like this, as I said before. So these are x, y data. X, y data. So pi is like a matrix. Okay. So now we have generalized this for all x and y. This became a matrix table. Okay, and this operations has been vectorized. This became a vector. So overall this is because our iteration was on the distribution itself, whole distribution, right? So hence we are producing these values. Okay. We went to pointwise because during optimization, pointwise values were easier, because pointwise optimality everything holds also for vector wise. So that it was okay for us to reduce. Now we go back to the vector vector notation. So that's it. That's an iterative way to find. Remember the problem that we were solving is like d pi. So basically we were looking for pi in the intersection of marginals this q, okay, and this is an alternating projection method that we used that projects between pi p as a affine set and in general convex set, and then goes to pi q, and it keeps doing this alternate. So pi will be guaranteed to be one of those which will be the joint probability with marginals both p and q, with marginals with both p and q, okay, and this is an iterative algorithm that leads us to that, okay. So so similarly we can also write this with very similar notation, that the odd will be L plus 1 and this becomes even, so L, that's it. And for the odd it's like the 1 gets transposed from this side, okay. So you can like verify this as well. So the odd iterations will look like this. We can carry the same argument. We started with pi p, but we can carry the same argument, exactly the same argument, to arrive at the odd iterations, because it's when you are going for p, you are doing the row sum, right? So that's 1 because you are looking for marginals in p. So you are doing row sum. That's why the 1 is coming here. And when you are projecting on the q, you are supposed to do column sum. So column sum is equivalent to multiplying vector of all ones from the left. Okay, then it does, then add column. This one multiplies to the other, and then it does the column sum and so on. That's why it gets reversed in the other case. Similarly, pi 2l plus 1 lambda is diag of q by 1 n transpose by 2l lambda and by 12 lambda. Okay, so this is our iterative algorithm. So I have to stop here obviously, but but this is not the end of this chapter. In the next class we are supposed to do in fact a more tractable algorithm that I could not complete, which is called sinkhorn, which is very simple, okay. So just that it's about time right now. So sinkhorn algorithm, which makes this algorithm even better, and then plus the generative modeling after that. So our goal in this course is to develop generative model. So this will be done in the next class. Basically 15 minutes, half an hour will be needed to do this in the next class. So what we have learned today is that we can tackle the Wasserstein distance as a generic optimal transport problem. It is a linear programming problem, but it's not tractable in the general form. And this problem can be changed into a KL divergence term via Gibbs distribution, and then we are essentially asking for a joint distributions which could be seen as intersection of marginal distributions, and hence it becomes a problem of finding a intersecting point between two convex sets. So these affine sets are essentially convex, and hence we go via this alternating projection idea, which goes to the intersection. Now one can prove additionally that this is an optimal solution in the sense that it's not just the intersection, but it's also a good solution, okay. So one can prove that as well. So we will see that we will try to see if we can do that in the next class, and we found an algorithm for the projection idea. So this essentially we have a way to compute costs like this. So this could be used as a cost function which is tractable, and for a certain theta I generate and check whether my cost is good. If not, then I go back, modify my theta with gradient descent and keep doing that. So essentially my generator, which takes Z, and this is my p theta, that produces the distribution p theta. This is a neural network model, and it's always compared with the p as a loss function, and then I keep checking, and then I will keep modifying my theta. So at some point what would happen is that this will learn theta in a good way, the parameters of the model will in a good way, that it becomes a generator. So now each time I will sample something from 0, 1, and if I train this on the true data, which is with scatter distribution, then the function has learned in such a way, each time I generate this, it knows how to generate some new interesting distribution. That's how the generative modeling will work. It works via the fact that I can directly compute the Wasserstein distance in a cheap way, which in general was not possible, and WGAN people have used some other variants. Okay, so with this we will stop. We have not done a key algorithm, which is synchron algorithm, and the generative modeling in the next class. Okay, so we can stop. Thank you.